Hello students, I just want to do a quick review of orders of reaction and what that means macroscopically, symbolically, and at the molecular level. So first we're going to start with some data. Let's say we have a reaction A plus B plus C makes D. Very creative, I know. Now we're going to do several trials here. We're going to be changing the concentration, the initial concentration of A, B, and C, and we're going to be measuring the rate. So for our first trial, let's have 1 of everything. When we measure the rate, we're going to say it's 5. Maybe this is like molar per second or something like that. That doesn't make any sense, but whatever. We'll just work with me here. Let's do molar per minute, okay, or molar per hour, because 5 is a big number. Okay, so we'll do this first trial. That's sort of establishing the baseline. These guys are each 1 molar. Now we're going to do a second trial. This time, we want to double the amount of A, but keep the amounts of B and C constant. And we notice when we do that, the rate actually also doubles. In the third trial, we're going to double the amount of B, but keep A and C at 1 molar. And in this case, the rate went up to 20. And then the last trial we're going to double the amount of C, but keep A and B at 1 molar. And in this case, the rate was 5. So let's break this down. There's a couple of things that we want to notice about this. So first, let's look at trials 1 and 2. In trials 1 and 2, we double the concentration of A. And the result is that we double the rate of the reaction. This is actually the first piece of evidence that this is first order. First order with respect to A. Let's just write A. First order with respect to A. Now, this means a couple of things. First, it means this macroscopic thing. This is our macroscopic thing. Macroscopic. Okay, that is a thing that we would observe, or data. We know that when we double the concentration of A, we double the rate of the reaction. That was what allowed us to conclude that this was first order with respect to A. Now we also have a symbolic way of writing this, or a mathematical way of writing this, and that's to say rate is proportional to the concentration of A raised to the first power. That first, this 1 here, is because it's first order, okay? And then the third way is that in the collision in the rate limiting step, and I know in my class we haven't gotten to rate limiting step yet, but accepting that reactions often occur in multiple steps, one of those steps will be the rate limiting or rate determining step. It's the slowest one. And what this is telling us is that in the rate limiting step, 1 molecule of A is involved. Okay, so 3 ways to think about it. This last way is the molecular way. So macroscopically, we double the concentration of A, we double the reaction rate. Symbolically, rate is proportional to A to the first power. And molecular level, in the collision in the rate limiting step, I need 1 molecule of A to be in that collision. So that's the first thing. We've looked at A. Now let's look at B. For B, we're going to look at trials 1 and 3. And we'll notice in trials 1 and 3, A and C are kept constant, but B is doubled. And when we double, so this is our macroscopic, we double the concentration of B, that quadruples the rate. It went from 5 to 20. So that tells us this is second order with respect to B. If we wrote this out symbolically, we would say the rate is proportional to the concentration of B raised to the second power. That 2 there is telling us this is second order. And finally, in the collision, in the rate limiting step, we need 2 molecules of B. And that's, again, our sort of molecular explanation. It tells us sometimes we use the word molecularity, the molecularity of the reaction. Now, we're going to look at the last set here, trials 1 and 4. When I look at trials 1 and 4, my macroscopic observation is that I doubled the concentration of C, and there was no change to the reaction rate. And that's a sign that this is 0 or 0th order with respect to C. Symbolically, if we were writing our expression, our rate law, we would say the rate is proportional to the concentration of C raised to the 0 power, or in other words, that's just 1. And our molecular level explanation, in the collision, in the rate limiting step, 0 molecules, that's a 0. 0 molecules of C are involved. Okay, so 3 ways to think about order. The most obvious is probably this macroscopic way. When I double the concentration, what happens to the rate? And then we have the symbolic way, which is also familiar because we see that in our rate laws. And then the last one is the molecular level, maybe the least familiar, but that's telling us when we know the whole mechanism of the reaction, we can determine how many molecules of each thing have to be there. Now, I want to talk about C for a minute. We said there's 0 molecules of C involved. That doesn't mean that C is not involved in the reaction at all. In fact, it's a reactant, and the reaction wouldn't happen if we didn't have C. However, it means that the place where C is involved in the mechanism of the reaction is not the rate limiting step. So it just must collide in there somewhere, and it happens really fast, and it's not going to be the thing that determines the rate of the reaction. It's still important for the reaction to happen, but it does not affect the rate. Now, the last thing I want to do here, we've got this information about A, B, and C, so we can actually write a rate law. Now, we found that it was first order with respect to A, so we'd say rate equals K, our rate constant, times the concentration of A raised to the first power, which we usually don't write, and then times the concentration of B raised to the second power. That would be our rate law for this reaction. And this is a nice summary here showing us that we need, in our rate limiting step, 1 molecule of A and 2 molecules of B. Those are all going to be involved in the rate limiting step, in the collision that is ending up determining the rate for that reaction. So that's a summary briefly of orders of reaction and how they manifest, the kind of 3 different ways that we think about the orders of reaction. If it's first order, that means we double the concentration, we double the rate. Second order, double the concentration, quadruple the rate. 0 order, double the concentration, don't change the rate. If we think about it symbolically, it changes the exponent in our equation. First order has an exponent of 1, second order has an exponent of 2, 0 order has an exponent of 0, or you just don't write it in the equation at all. And if we think about the collision that's in the rate limiting step, it also tells us the molecularity. In this case, 1 molecule of A and 2 molecules of B and 0 molecules of C are involved in that collision. Okay, that's everything.